Hello students, I am Dr. S.L. Munde, Assistant Professor and NSS Program Officer, Department of Mathematics 3, RLT College of Science, Akola. Dear student, in previous lecture we have completed unit number 1, that was the complex integration. So from today in this lecture we will start unit number 2. So in unit number 2, the first topic is maximum and minimum modulus theorem. Okay, so in this lecture, in first point or in first topic, we will see maximum modulus theorem, then we will see minimum modulus theorem. Okay, so in examination, there may be the question state and prove maximum modulus theorem. So in this examination there may be the question state and prove maximum modulus theorem. So what is the statement of the maximum modulus theorem? So if f g to c is a analytic function where g is a region and a is a point in a region g with mod f of a greater than equal to mod f of z for all z in G, then we have to prove that f is a constant function. So this is the statement of the maximum modulus theorem. Okay, so now we will prove this theorem. So let us suppose that what is we have given? We have given f g to c. So here f of z is a function, g is a region, and c is a complex plane C. So let us suppose that f g to c is an analytic function where g is a region, and let us suppose that a is any point in a region G with mod f of a greater than equal to mod f of z for all z in G. Okay, so to prove this theorem, let us we consider a closed circle with a center a radius r in a region G where r greater than 0. Okay. So therefore f is an analytic function on a closed circle whose center a radius r, because f of z is an analytic function on a whole complex plane C. So therefore we can say that that function f of z is also analytic on a closed circle whose center a radius r. Okay, so therefore by using the Cauchy integral formula, f of a equal to 1 upon 2 pi I integral over gamma f of z upon z minus a dz for z minus a less than r. Okay, so we can write in this way. So where the curve gamma of t equal to a plus r e raised to power it, where a is the center of the circle and r is the radius of the circle, t lies between 0 to 2 pi. Okay, so therefore taking the modulus on both side, modulus of the sign on both side, so we get mod of f of a equal to mod of 1 upon 2 pi I integral over gamma f of z upon z minus a dz mod complete. Okay, so in this way we can write this term, okay, in modulus term. So by using the modulus property, so this can be written as mod f of a as it is less than equal to 1 upon, take the mod of the each term, so 1 upon mod 2 pi, that is 2 pi mod I integral over gamma mod f of z upon mod z minus a mod dz. Okay, to solve this integral, let us we put up z equal to a plus r e raised to power it. Okay, because z is a lies on a curve gamma. So differentiate with respect to t. So dz equal to derivative with respect to t, that is 0 e raised to power it r into e raised to power it means derivative of e raised to power it, that is r e raised to power it, and this is r as it is dt. T lies between 0 to 2 pi. So put this in above equation. So mod f of a less than or equal to 1 upon 2 pi. The value of modulus of I, that is 1. Okay, we know that the concept of the modulus term. So integral this will become 0 to 2 pi because we are integrating on t. So t lies between 0 to 2 pi. Mod f of a plus r e raised to power it, that is f of z, z means a plus r e raised to power it, divided by z minus a. Z minus a means that is a plus r e raised to power I t. So a will get cancelled. So only remaining is mod r e raised to power I t into dz. Dz means ri e raised to power I t dt. So here mod ri e raised to power I t dt, ri e raised to power I t will get cancelled. So what is the next steps? So which implies mod f of a less than or equal to 1 upon 2 pi modulus of I is 1 integral 0 to 2 pi f of a plus r e raised to power I t dt, equation number 1. Okay, now we know that we have considered a closed circle whose center a radius r which is containing in a region G. So therefore z equal to a plus r e raised to power I t for all z belongs to G. So which implies mod f of a greater than or equal to mod f of z. Okay, so this can be written as, which implies mod f of a plus r e raised to power I t, put the value of z, so less than or equal to mod f of a. We can write this term in this way. Okay, so now multiplying on both sides by 1 upon 2 pi and integrating with respect to 0 with respect to t or 0 to 2 pi, we get 1 upon 2 pi integral 0 to 2 pi f of a plus r e raised to power I t less than or equal to 1 upon 2 pi integral 0 to 2 pi mod f of a dt. Okay, so less than or equal to 1 upon 2 pi, this can be written as it is. So this mod f of a is a constant term, so take outside of the integral. So 0 to 2 pi dt, the value of this integral is, that is t, and upper limit minus lower limit, so this will becomes 2 pi. So this 2 pi and this 2 pi will get cancelled, so what is remaining is 1 upon 2 pi integral 0 to 2 pi mod f of a plus r e raised to power I t mod complete less than or equal to mod f of a, equation number 2. Okay, so now from equation number 1 and 2 we can write, or we get, or we can say that mod f of a less than or equal to 1 upon 2 pi integral 0 to 2 pi mod f of a plus r e raised to power I t mod complete dt less than or equal to, and this is nothing but less than or equal to mod f of a from equation number 2. Okay, so by using inequality we can write 1 upon 2 pi 0 to 2 pi f mod f of a plus r e raised to power I t dt equal to f of a. Okay, so we can write in this way. So 1 upon 2 pi 0 to 2 pi, this left hand side as it is equal to 1 of that mod f of a, we can write in this way. So if you solve this integral, so you will get the value of this integral is, that is 2 pi. So this 2 pi will get cancelled. What is only remaining, that is mod f of a. So we can write mod f of a in this way, Okay, so take in left hand side, transfer this term to left hand side and take 1 upon 2 pi is common term and integral is 0 to 2 pi is common term, and take this term in one bracket. So 1 upon 2 pi 0 to 2 pi integral in first bracket mod f of a plus r e raised to power I t mod complete minus mod f of a bracket complete dt equal to 0. So you can write in this way. If you transfer this to LHS side and taking common 1 upon 2 pi, and integral will be the 0 to 2 pi common integral. Okay, so but we know that mod f of a plus r e raised to power I t minus mod f of a is a positive, and it is the integrated in the interval 0 to 2 pi. This will be the positive value. Okay, so therefore the which implies the mod f of a plus r e raised to power I t minus mod f of a equal to 0. Okay, so after if you solve this integral, okay, if you solve this integral, so you will get this term. Okay, so which implies mod f of a plus r e raised to power I t equal to mod f of a for all the values of t equal for 0 less than equal to t less than equal to 2 pi. Okay, so but a plus r e raised to power I t t lies between 0 to 2 pi is any point lies on a curve gamma. So therefore we can say that that is the point which is lying on a boundary of the closed circle whose center a radius r, and r is an arbitrary which is true for the any point in region G. Okay, so therefore mod f of z equal to mod f of a for all the values of z in region G. Okay, so here f of a is a constant function, so therefore we can say that mod f of z is a constant function. So which implies f of z is a constant function, or we can say that f is a constant function. Okay, so this is the theorem, maximum modulus theorem, complete proof of the maximum modulus theorem. So dear student, you have to note that the maximum modulus theorem is also stated as if analytic function can be take the maximum value at any point inside the region G, then that analytic function must be a constant function. So this maximum modulus theorem can be stated in this another form. Okay, so again another statement in another word, the maximum modulus theorem can be written as analytic function never takes its maximum or minimum value inside the region G. Or third, also maximum and minimum value are attained at the point on a boundary. Okay, so these are the different tests of the statement of the maximum modulus theorem. Okay, you have to note this three note. Okay, now we will see the second theorem, that is uh, minimum modulus theorem. This is not a maximum, minimum. So here we have to take the minimum modulus theorem. State and prove minimum modulus theorem. Minimum modulus theorem. Okay, so what is the minimum modulus theorem statement? Let f g to c is an analytic function on a bounded region G with mod f of z is not equal to 0 for all z belongs to G. Then f of z or f cannot attain its minimum value at any point inside the region G. Okay, so this is the statement of the minimum modulus theorem. Okay, this is not a maximum, this is the minimum modulus theorem. Okay, now we will see the proof of this minimum modulus theorem. So what is given? So we have given f g to c is an analytic function on a boundary region G with mod f of z is not equal to 0 for all the values of z belongs to G. Let us reconsider equation number 1. So to prove this theorem, let us define another function, that is g in the region G in a complex plane C on a complex plane C such that g of z equal to 1 upon f of z. Let us consider equation number 1. Okay, so it is clear that from this equation number 1, it is clear that the g of z is well defined because f of z is an analytic function, and therefore we can say that g of z is a well defined function. Okay, if f of z is analytic function, then we can say that g of z is also analytic function. Okay, so since f is a analytic on region G, this is given, therefore we can say that here g of z is a well defined. So therefore there exists g dash of z derivative of this term. Okay, so therefore g dash of z equal to derivative of this term, that is 1 minus 1 upon f of z bracket square into derivative of f of z, that is f dash of z. Equation number 2. Since we know that f and f dash are the continuous for f of z not equal to 0, so therefore we can say that g dash of z is also continuous. So which implies g of z is also a continuous function. So which implies g of z is analytic on region G because f of z is given is analytic. So therefore we can say that g of z is also analytic on region G. So therefore by using the maximum modulus theorem, g of z cannot take maximum value at any point inside the region G. Okay, so here we are using note number 3. Okay, so by using the maximum modulus theorem, g of z cannot take the maximum value at any point inside the region G. Okay, so but the maximum value of g of z is nothing but the minimum value of f of z. Maximum value of the g of z is nothing but the minimum value of the f of z by the definition of the g equal to 1 upon f of z. Okay, so therefore f of z cannot take its minimum value at any point inside the region G. Okay, so this is the proof of the minimum modulus theorem. Okay, so this is the statement of the minimum modulus theorem, and this is the complete proof of the minimum modulus theorem. Okay, so in next lecture we will see the next point of this unit number 2.